All right, welcome everyone. This is our panel on how AI is upgrading AV development. So I'm hoping this is going to be one of the more technical panels of the day. So I hope all our panelists can define their terms and try to avoid jargon as much as possible. Let's do a lightning round of introductions down the line here.
Thanks, Rocket. I'm Oscar. I run the solutions engineering team over at Encord, and so we handle everything on the kind of data development side for physical AI. So from managing, curating, and then also annotating and running evals and stuff.
Yeah, I'm Soroush, co-founder and CEO of Aeva. We're a publicly traded company on NASDAQ focused on sensing and perception, bringing next sensing, LiDAR, and software to physical AI applications, automotive, robotics, manufacturing automation, as well as defense and other applications.
Good afternoon. My name is Erik, and I'm CTO at Zenseact. And Zenseact is a company developing a software stack for vehicle automation and active safety and a part of the Volvo Cars group.
Hey folks, my name is Anu. I'm a field engineer with CoreWeave, and I specifically focus on everything we do with embodied AI. So AI, once it gets a real physical body to work with things.
Perfect. OK, so yesterday I was looking over the physical AI news of the day, and I saw that DeepMind released a new physical AI model. They did Gemini Embodied Reasoning 1.6. So it's a vision language model that's designed for reasoning about the physical world. So I saw this, and my impression is that these kinds of models are improving pretty rapidly, but I don't know if they're production level yet. So I'm curious about your impressions about this. Maybe one, I would be fascinated to learn if anyone has used that model or intends to use that model. But more generally, what is the role for language and reasoning in the AV stack?
Yeah, so I can start. I think that model that was developed in partnership with Boston Dynamics, and where it was especially the incremental improvement there above Gemini Flash 3 was its ability to actually spatially reason, and so kind of see in that perspective. And there's been a bunch of kind of conversations today about different model stacks and teams that are using kind of multiple models and then full end-to-end systems. And I think part of the piece as it relates to AV and safety is being able to get these outputs that you can kind of quantify. So it's like if you have a full end-to-end system, being able to bring out multiple different outputs throughout this pipeline. And so I think having more explainability, more spatial reasoning helps with that.
Yeah. Any other takes or reactions to that?
I didn't know it got released. I was still on the wait list, so I need to go try it.
I've not tried it either, but in general, I mean, these kind of foundational models or world models, if you want, I think it's a super exciting development. It's probably very researchy still, but it is something that is powerful. I mean, we as humans use something like that when we solve problems in the physical world. And we've seen NVIDIA with Alpamayo, some reasoning capability in there as well. So I think it's really exciting to see where that is heading. But I do still think it's a little bit researchy. It's not something that at least we would put in a stack today.
Yeah, and Alpamayo as well, I think, had more of that reasoning that was transparent. It was visible to the operator, so you have a little bit more interpretability built in.
Yeah. I think one of the key things is with some of these world models, as they're advancing, the ability to swap in different data streams and inputs has become pretty important. And I think in the first wave, for folks who've been in the industry for 10, 15 years, for AVs at least, it was pretty difficult and cost intensive to swap out, let's say sensors. Even if you need to go to the next computer, how you retrain, new data with new models had been a challenge. But I think with these advancements, yeah, it is researchy, but I think it is enabling these new entrants to actually come up, and some of them achieve performance parity with folks who've been in the business for years with a lot more investments. And that's what's exciting, I think, about this. The other piece I think it says, as Erik mentioned, is I think it enables AV developers, OEMs as well, to then iterate faster and help address those corner cases. And we have seen that with NVIDIA Alpamayo. I think it is been a pretty successful collaboration so far between Mercedes and them. And we work with NVIDIA as well, and we see that now going from camera-based for level 2 to enabling level 3, which requires other sensors like LiDAR as well.
Okay. Yeah, let's talk a little bit more about world models. I mean, do you all see that as a promising direction? And is there something you're hoping to get out of world models in the next year or two, either as simulated training environments or running on the edge? What are you hoping to see there?
I think one of the biggest differentiators for the teams I'm working with comes from the ability to generate a lot of data they didn't have in the past. Like, if you saw the announcements at GTC, a lot of that was focused around the synthetic data generation pipelines, models, and how this is going to enable teams. I know, your team at Encord is doing a lot of work with that for doing data curation pipelines. I think what these teams are struggling with is if you're OpenAI and you're going to go train the largest LLM possible, there is a lot of text data out there to do that, but there's a lot of labeled image data out there. When it comes to video, we're reaching a point where we have an insane amount of video available. Like YouTube's got terabytes coming every minute, every second. But to curate that into something a model can ingest is still a big blocker. And that is a very resource GPU intensive process. So solving for that becomes the biggest challenge for a lot of these teams. World models really help with closing that gap. Like, we're creating a lot of data that we can use now, but how do we make it useful in an actual training pipeline?
What do people think about that? How do you make it useful in a training pipeline? What's the answer? What's missing right now?
I mean, I'm happy to go. I think from that perspective, the world models that we see teams using, that they're really good like generalizers, and also for data generation as well. As Anushrav mentioned, then like that is super helpful for being able to kind of test these situations and run these experiments. But we also see teams looking at the kind of outputs and the reasoning in these pieces from like edge cases as well. And there's been a few mention of the kind of long tail of these data distribution pieces, and that's where running world model processes can be really helpful. The only caveat I would say is, because often they're kind of compared to like VLAs, is that VLAs are generally quite, we see teams that they find them very helpful for looking at breaking down subtasks over kind of smaller, more narrow scenarios, rather than world models, which are really good like generalizers over the top.
Got it. All right, well, that covers vision, language, reasoning, world models pretty well. I'm curious to throw out a few other categories of foundation models, and I'm interested in your thoughts of, do you think these are very promising directions to go in our current margins? They're very useful, or maybe they're not useful at all? So I'm thinking like better segmentation models, maybe better agents, maybe VLAs as well, vision language action models. Are these promising or not so useful?
I think it's promising. The fact that you can learn from text, or there's so much knowledge stored in text and in VLMs that you can leverage when you're building your AV stack. And it somehow feels like it provides you scaffolding. So when you're actually training your models, there's already some form of scaffolding that helps you in the training process, which is really good. But I also like the fact that you can use this for understanding what the model actually does, some form of interpretability of the capability of the stack. I think that's going to be important when you either develop, or in case something went wrong and you want to understand why is it happening, and these kind of models will help you with that kind of things.
I think one of the other things is when you look at the models, if you put the underlying blocks of what makes a specific model, I think one piece of it is how do you validate like the use cases, especially for autonomous vehicle. I mean, this is a physical world thing, right? It's very different. You're not like interacting in like behind a computer, right? And safety is super critical, So that's, I think for folks that have been with OEMs for quite some time and interacting with it, the ability to verify and validate individual blocks or inputs and outputs has become pretty important. Working with partners, suppliers from the OEMs, we're on the other side of that. We see that, you can look at using maybe simulation tools for creating a bunch of scenarios where it's costly to make those scenarios in the real world with the actual data from the let's say, the sensing inputs and what you actually have there. So I think the question has been more around like, okay, like how many hours is sufficient to get there from a data curation standpoint? Okay, you get many OEMs need at least 1,000 plus or thousands of hours of real world data across the world in different geographies to validate, let's say, a certain type of functionality, right? Let's say like, highway level 3 driving. And I think regardless of the models and the foundation of that, I think that the data set and how you actually implement that from the sensing side has become, I think, pretty important. And I think we're seeing more and more maybe reliance on partners rather than, that's basically the tier 1 suppliers rather than the OEMs themselves to make that happen. And I think, I'm curious, I don't know if you see that because you're between the OEM and...
we are really close to Volvo Cars. But we leverage the fact that there is a fleet of vehicles out there very much. Maybe it's the Tesla model. Our stack is running in many vehicles and is being produced. We can get data from the fleet. And the data we can use then for training our models. And that's, of course, super useful because edge cases happen every single day all around the world, and you get a really good spread in that. But still, you want to leverage that as good as possible when you then train your model. So here, some form of data augmentation is really helpful to make sure that the stack is robust and generalizes well across everything that happens in the real world.
Yeah, and I'll just add one thing to that. That's where world models, just going back to that idea, become really powerful, right? Like you find out in simulation, in real world testing, something doesn't work. Generating specific data to do that job, to train your model in that edge case can be expensive. You're not going to send out a new car to collect new data, but you can do that so much faster in these synthetic data generation pipelines and get that exact data to improve your model. It really helps cover up those edge cases really fast.
Yeah. Well, you might wonder then, we have all these amazing models. We have the ability to augment data from the real world. We have cars that are deployed. The data flywheel is turning. What's missing? Like, what stands in the way of having self-driving cars in every city and also on rural roads and in other kinds of environments like construction sites and so on? What's standing in the way?
I would say no matter, you have the best models, you have the best training, you have the best simulation, all that, nothing really beats the real world, however, right? So, and again, it's a physical world, right? Like, things go wrong, shit always happens, and you're never gonna catch all the scenarios, no matter like the best kind of, AI models and training data sets and whatever you have to use. So I think how much correlation you can provide and how much you can cover some of those corner cases, that's, I think, where it's exciting with these advancements, because the more you can cover, the less, the more confidence you have, and maybe the less you have to rely on the physical kind of validation runs, but you cannot completely replace it. I think one of the things that you asked about missing, I think, is actually, unlike language models, for the physical world, one of the key, I think, missing points have been the correlation of the physical sensor models, let's say. For me, I speak from the perception side, but from the physical, the physics-based modeling versus just, photorealistic or whatever it is on these, on the sensory input. So how you make sure that what you're actually augmenting in simulation and in the data set is seeing the photons the same way, let's say, that the sensor is seeing. And that's not trivial. This is pretty challenging. And there's always simplifications. The world of optics, there's many layers of simplifications needed to make it fit into a compute-intensive model. So I think that's an area where I wish there were more companies that are resolving that. I know there is like a handful of companies that are working on IP in that area, but until you have that close correlation between physics simulation for the, let's say, each sensor model, I think you will always have gaps where like some corner case you may not pick up. Like it may work really well in the simulation and it completely craps out in the real world.
So validation, is one of the key bottlenecks. It's hard because the real world is so complex and it's so big. We operate in personal cars that are being sold all around the world. So you see data from all around the world, and then you realize how big the world is and how different traffic can be and how different weather conditions can be. So that makes it hard to scale because it's a safety critical application as well. If you make a mistake, it has or can have very severe consequences.
It's like playing GeoGuessr all the time.
It's a way of becoming really good at that.
Yeah. Oscar, I'm curious about your reaction. I mean, does it all come down to real-world data at this point? That's kind of the bottleneck. That's the limiting factor on deployments?
I think when we're building these systems, and so we work with teams who have all sorts of different like sensor configurations. Some have lots, some have few, but I wouldn't get in a self-driving car that hadn't been validated in the real world, right? And so we're talking about all these unusual edge cases and all these kind of examples that we see. So like you can solve for a very large corpus of these in testing and with synthetic data, but then in order to actually validate this, like you need that real world output, and you need a way to be able to explore that, so actually find those long tail pieces and then also address them. And the only way at the moment you can do that with 100% reliability is with human context. And so actually human input to say, okay, this is what happened in this case, being able to monitor those tests.
Anushrav, does that line up with what you tend to hear from customers?
That's true. Like, nothing beats real world data. I think a lot of the problems that synthetic data is solving is that early development stage. Yeah. You're starting an AV company today, your first 5 years will all be in synthetic data, or like, really any physical AI company. But then once you reach a point you're trying to deploy in the real world, all those edge cases, your perfect photorealistic renders from your world models never showed you, start popping up. These are glares, these are reflections that, that will trip up your sensor that you just don't expect these world models to even generate in the first place.
You don't even expect them to. Like, it's not a problem that we're trying to solve with AI. That's sort of the wrong tool to solve the problem.
It's only solving a part of the problem.
Yeah.
The other part will come in the real world as you try to build things out. And I think, if you look outside, like that's one of the biggest advantages for companies who have a physical car out there on the streets right now collecting real data and testing on it versus anyone that's still in the lab. That gap keeps widening over time. So those companies have to work a little bit harder to get their technology to a point where they'll compete with these massive swaths of private data sets that are built up.
Yeah, I'm curious for all of you if there are other places where you think throwing more AI at the problem is not the right approach. Maybe like Soroush, to start with you, like are there problems that need better hardware? It's not about better AI, it's like better hardware is needed.
Yeah, I think, it's the age-old question. Work at a company that's making LiDAR, right? So that's, I know that question is coming, so I will talk about it. But I think, absolutely. I think the one clear example is no matter how good of an AI you have, if you have garbage in, you will not have gold out, right? So you may have something closer to a garbage out, maybe, better, but. And okay, that's an exaggeration example, but if you cannot see something in the physical world, the best AI model cannot generate that, right? So that's where like physical sensing becomes critical. So I think that's why advancements in perception doesn't only rely on advancements of AI. I think it's hugely improved by advancement in AI, because then what you actually can do is, and maybe this will helpful for others that are in the OEM side can see that is you don't have to keep spending a ton of money on very advanced GPUs. You can get by with lower cost processors in the computer, and you can push up some of that inference on the edge, and that's where all the edge AI is happening. This is the future of physical AI. It's coming, and for that means you need to have better sensing solutions, and that's where perception comes. So in our case specifically, if, for example, we can measure, we have a technology called 4D sensing, 4D LiDAR. So we can measure velocity in addition to distance. It's kind of a combination of LiDAR, radar in some ways. And what that means is, okay, let's say at 300 meters, if you, first of all, if you have a camera, you may not see that object per se. We can argue about that at length at a different time, but if you have, let's say, a traditional kind of LiDAR sensor, you may see a few points on it. All you can do at that point is, okay, is that an object Is that 5 objects? Is it noise? So what you can do is you can keep looking. That's all you can do. But if at the same time with that 4th dimension that you can get the velocity information, that's speed of the object, then you know, do they all have the same speed? That means it's most likely one object. If they all, as a cluster coming towards you at 80 miles an hour, that's a damn car, you better watch out, right? And you can make that decision, and the stack can make the decision very quickly after the first 1 or 2 frames. And that, I think, is a differentiation in safety reaction, safe stopping distance, which becomes critical for long-range applications, including trucking and some of the other stuff. So that's a very clear example of best AI doesn't always solve it. Of course, it helps, but it's not actually, sometimes brute forcing it is actually the wrong answer. So I think we are excited about the advancements on the hardware side. And as you go more towards silicon photonics and reduce costs, the argument of do you need a LiDAR, who cares? If it's a couple $100 and it's not visible anymore like an ugly thing on top of the car, why not?
Erik, what do you think?
No, but I agree. I mean, better sensing will definitely help. But also simple things like having hardware to clean a sensor will help. I mean, you can do a lot of things with AI, and probably the biggest promise is through AI or through software. I mean, the potential there is huge, but it doesn't mean that there is not the potential in building better products through better hardware. I mean, of course, you have to work on all fronts.
And as we keep updating software, right, like you mentioned, all these new frontier models coming out, foundational models to improve the quality of the overall product we're building as an autonomous system, as an AV. I think these better models do play a role. Because if you think about it, we can always consider like the AI model is the brain of the entire system, but just like our brains, it's split into multiple parts. There is perception, planning, action, and having a specific model that excels at that is a really good way to build a cohesive system that works really well in the end. And I think that's what a lot of teams are trying to build towards. So as more research comes out of labs with new architectures, new models that can be just a little bit better at the specific task of sensing, segmentation, that has trickle-down effects in the overall quality of the system we're building that can be fully autonomous.
Absolutely, and I think to that point, when you have these systems, and whether they are separate perception and planning systems, or it's a kind of unified model that's taking in multiple different data modalities and whatever, if you increase the resolution of the data, then you can improve the ability to do both of those tasks, so long as you have the right context, right? So it's like, as long as you have if you are separating what is noise, what is blur, what is an actual object, what is 3 objects, you need to be able to give those models that context, and that ultimately all comes down to the data. And we see teams using a combination of models and humans for that kind of like context generation ultimately.
Yeah. My last question then that we can end on here is, as we're moving more and more to these end-to-end approaches, which are less interpretable, and sometimes they misgeneralize in weird ways when they encounter edge cases, what does it mean for an AV company to develop a safety case for their car before deploying their car and getting it out on the road? Both in the sense of what would be a compelling safety case to you as an expert, but also what kind of arguments do companies need to present to the public that will be compelling to the public?
I mean, maybe something that is especially important when you have more AI and go end-to-end is having some form of understanding why the model does what it does. I think things will go wrong. I mean, we will do everything, everybody's working to make sure it's really, really safe, but one day accidents will happen. And then you will get the question, okay, but what happened? And you'll need to get some understanding of what actually happened. So some form of interpretability of your model you need to get. But also you'll get the question, how do you make sure that this will never happen again? Then you better have a good answer, and you have a better good idea on what you will do about this, because those questions will come. And here I think things like interpretability or having some form of introspection into the model and what it actually does and doesn't do is going to be very important.
I think we're still really early on model reasoning, things like Shapley and DRISE algorithms that really help you understand what the model sees and what it indexes on to make a decision. And that research is so far behind. I don't think there is an answer coming from research or labs for this. It's very much a policy answer right now, like who do we go blame or who do we ask for answers? The technical answer, I hope we have in the future. so we can really find out what went wrong with the models here.
Perfect. Well, I think that's all the time we have to talk, so we'll end on that note. Please join me in giving a round of applause to our panelists.
Thank you. Right.